This is Chapter 3 of the Inorganic Chemistry course. I've divided it into two parts. In this first part, I am going to move through it fairly quickly. It is the most basic chemistry that you would have taken in your very first chemistry course in high school. So you can decide how much time or how little time you choose to spend in it, but don't leave this chapter without knowing how to write the Lewis symbols of the representative elements and what they mean. When chemical reactions occur, it's because atoms gain, lose, or share electrons. If we're going to understand chemical reactions, we have to learn the distribution of electrons within atoms. You've heard me say that before, right? So these are Bohr diagrams of the representative elements, the A group elements. So I'll read a little bit here and then we'll go right to drawing some of these. Bohr diagrams show the arrangement of electrons in the atoms, and each shell can hold up to a certain number of electrons and no more. For example, the first shell can hold a maximum of 2 electrons. The second shell can hold a maximum of 8 electrons. A Bohr diagram shows how many electrons are in the shells surrounding the nucleus. The Bohr diagram is named in honor of Niels Bohr. So in the diagrams that follow, called Bohr diagrams, that you can see below, they show electrons as dots arranged in circles, and these circles represent the shells around the nucleus. Now they're only simple models, they're not necessarily accurate, but they are useful. Let's go to page 72. Let's draw the Bohr diagrams for the first 20 elements of the periodic table, the representative elements. So we'll draw the symbol. Start over here in group 1A. This is hydrogen. It has 1 proton and 1 electron, so I'm going to draw a single dot, and that's its single electron. That would be described as 1s1. We're not supposed to know this, but we've already taken it. If we slide across to the right side of first period, we'd have helium with 2 protons and 2 electrons, and we're just going to pair those 2 electrons up because that first shell is now full and the orbital is a 1s orbital and it's full. Let's go to lithium. Lithium is in the second period. We would write its symbol like so. I've already provided the 2 electrons that are in the first shell. Just draw the third electron, which is in the second shell. So notice that, like hydrogen, lithium is in group 1A and has 1 electron in its valence or outermost shell. After lithium is beryllium, element number 4, 4 protons and 4 electrons. Now, when we put the second electron into the second shell, we're going to spread them out rather than pair them up. So let me slide to the bottom of the page here. We mentally draw straight lines to divide the second and third and fourth and higher shells into 4 subshells, which we call orbitals. So think of these positions as being orbitals. We learned about the s, px, py, pz orbitals. We draw 1 in the north, 1 in the south, 1 in the east, 1 in the west. And each orbital can hold a maximum of 2 electrons. The first shell, that'd be n equals 1, is the smallest. It only has room for 1 orbital, so it can hold no more than 2 electrons. Now remember that electrons are negatively charged and the protons in the nucleus are positive. Opposite charges electrostatically attract each other, so electrons will of course fill the inner shell first, and that's the Aufbau principle, building up. Second and higher shells, n equals 2 and n equals 3 and n equals 4 being larger, have room for more orbitals. Electrons will spread apart when possible because they are all negative and like charges repel, so the 4 orbitals of each shell are singly filled before pairing. Now I know this is not exactly correct, right? We know that the s would fill before the p, but the Bohr diagrams, rather than showing the ground state electron configuration, they show the electron configuration when an atom is about to bond. And when it's about to bond, electrons in the outer shell will spread out. And the reason for that is they want more room to attach other atoms, and more room means they spread out. So think of it not as the ground state electron configuration, but rather a configuration that's changing as it's just about to bond. So boron, 5 protons, 5 electrons, 2 in the first shell. Remember, we're mentally dividing our second, third, and fourth, and so on shells up into 4 parts. So put 1 in one location, 1 in another location, and we have 3 in the outer shell. Now the exact arrangement, whether it's clockwise or counterclockwise, doesn't matter. Just 1 in each of 4 locations, 1 in each of 4 orbitals. Carbon is element number 6. Here's its Bohr diagram. Nitrogen is element number 7. Each of the 4 orbitals are singly occupied, and then we have to pair them up because there's only 4 orbitals in each shell. Oxygen is next, element number 8. 2 electrons in the inner shell. We'll have 6 in the outer shell. I'm going to put 2 pairs, top and bottom, and then singles left and right. Next is element number 9 is fluorine, with 2 electrons in the first shell and then 7 in the second shell. So each of these is singly occupied, then they have to pair up. Alright, so we have the second shell is almost full. When we get to neon with 10 valence electrons, 2 in the first shell and then 8 in the valence shell. Neon is a noble gas. It's unreactive. Electrons will not be gained nor lost. There are no known compounds of neon. It exists as a monatomic atom. Likewise is true for helium. Sodium has 11 electrons. This is in the third period. So 2 electrons in the first shell, 8 in the second shell, and we have the 11th electron in the third shell. Notice the valence shell of hydrogen has 1 electron, and lithium, and so does sodium, and so their chemistry is very much alike because of that. Element number 12 is magnesium. Total of 12 electrons, 2 in the first shell, 8 in the second, and then 2 electrons in the third shell. Next we have aluminum, element number 13, 2 plus 8 plus 3. Next we have silicon, element number 14, 2 plus 8 is 10 plus 4. Now take a look, notice, look at the period above. The valence shell in the second period and the third period are identical. Carbon has 4 electrons in the valence shell. It's in group 4A, and so does silicon. It's in group 4A, and it has 4 electrons in the valence shell. So what does the A group number tell you? It tells you how many electrons are in the valence shell, which is really important. Below nitrogen in group 5 we have phosphorus, 15 electrons, 2 in the first shell, 10 in the second. It'll have 5 electrons in the valence shell. It's 2, 3, 4, 5. So that's what the group number tells us. It's group 5A. It's got 5 valence electrons. Next is sulfur. Sulfur is element number 16. 2 in the first shell, 8 in the second shell. It's going to have 6 electrons in the valence shell. It'll be just like oxygen. They're both in group 6A, so they have 6 valence electrons. Element number 17 is chlorine. 2 electrons plus 8 is 10, then 7 more. 1, 2, 3, 4, 5, 6, and 7. 1 electron short of a full valence shell, or a full octet. Argon, 18 electrons in total, 2 in the first shell, 8 in the second shell, and then the valence shell will have 8 electrons, and that's full. We say an octet is a group of 8. Turns out that any of the noble gases, all of the noble gases, have a full valence shell, and we attribute that to the reason they're so unreactive or inert. And other elements try to gain electrons, like the non-metals, to fill their valence shell, or the metals try to lose electrons to empty the outer shell so that its next shell will be a full octet or similar to the nearest noble gas. 2 more to go. We can put in the 4th period. We have potassium with 19 electrons, 2 in the first shell, 8 in the second, 8 in the third, that's 18, and then 1 more is 19 in the valence shell. And we'll go as far as calcium with 20 electrons, 2 and 8 and 8 and 2 more. So I'm repeating myself, but it's so important. Look down any column, the number of electrons in the valence shell is the same, and that's what really, really matters. That tells us the chemistry of the elements in that group. Everything in the second group, in group 2A, the alkaline earth metals all have 2 valence electrons, and that's their chemistry. Their chemistry is to lose those 2 electrons. In group 3A, we see we have 3 electrons in the valence shell. In group 4A, all elements have 4 electrons in the valence shell. In group 5A, all the elements have 5 electrons in the valence shell. In group 6A, all the elements have 6 electrons in the valence shell. And in group 7A, all the elements have 7 electrons in the valence shell. In group 8A, they all have 8 electrons in the valence shell except for helium, which has 2 electrons in its valence shell. And they're all full. Their valence shells are full. On page 73, I have the answers to the Bohr diagrams. So we're going to do another exercise on the next page. We're going to simplify the Bohr diagrams as I'm showing here. So this is the Bohr diagram of potassium, but we could simplify it. Instead of drawing dots, we could write the number of electrons in each shell. So in the first shell we had 2, we'll write a 2. Second shell we had 8, we write 8. And then 8 again for the third shell and 1 for the fourth shell. And rather than drawing a full circle, just to save space, we'll draw like a quarter circle or a half circle, whatever that is, and we'll put the element's symbol as if it were the nucleus. And that's called a simplified Bohr diagram, and it tells the same information, but it's a little simpler to draw. Let's try some of those. Let's start with hydrogen. 1 electron. Move over to helium. Looks like I already have a 2 in there. So the first shell is full, inert, and stable. Our next element is lithium. 3 electrons, 2 in the first shell and 1 in the valence shell. And we have beryllium. 4 electrons, 2 in the first shell and 2 in the second shell. Boron is next, with 5 electrons, 2 plus 3. Carbon is next, 6 electrons, 2 and 4 in the valence shell. Nitrogen, element 7, has 2 electrons in the first shell and 5 in the second shell. In the valence shell, the outer shell is called the valence shell. Oxygen, element number 8, 2 electrons in the first shell and 6 electrons in the valence shell. It's only the valence shell electrons that are involved in bonding for the A group elements. And so that's what we're focusing on, is only the valence electrons. Next we have fluorine, element number 9, 2 plus 7 in the valence shell, 1 electron short of a full valence shell. Next is neon, 2 and 8. So neon has a full valence shell. It's unreactive, stable. Let's move over to sodium, which is element number 11. 2 electrons in the first shell, 8 in the second, and then 1 in the third shell. Magnesium, element number 12. 2 electrons in the first shell, 8 in the second, and 2 valence electrons. Aluminum is next, 2 and 8 and 3 electrons in the valence shell. Silicon, element number 14, 2 plus 8 is 10, and 4 in the valence shell makes 14. Phosphorus has 2 electrons in the first shell, 8 in the second, and 5 in the valence shell. Sulfur, element 16, 2 plus 8 is 10, plus 6 in the valence shell. Chlorine, element 17, 2 plus 8 is 10, plus 7 in the valence shell. And next we have argon in group 8A, element number 18, 2 plus 8 plus 8. It's in group 8A, and that's why there's 8 electrons in the valence shell. 2 more to go. We have in the 4th period, we have potassium, element number 19, 2 and 8 and 8. In the 4th shell we have 1 electron. And finally calcium, 20 electrons, 2 and 8 and 8 and 2 in the valence shell. So again, I'm repeating myself, but notice that all the elements in the same column have the same number of electrons in the valence shell, and these columns, 1A, 2A, 3A, 4A, they tell us the number of electrons in the valence shell. And when Dmitri Mendeleev was trying to arrange the periodic table in some meaningful fashion, he didn't know about the position of electrons. He just arranged the elements according to their behaviors. And later we found that the elements, when arranged in this fashion according to their behaviors, showed similar electronic filling arrangements. Page 75 has the answers to these simplified Bohr diagrams. So here I've drawn the Bohr diagram and the simplified Bohr diagram and the Lewis symbols for the first 20 elements, at least as many as I could fit on the page, just to compare. So take a look at one. So notice all 3 of these diagrams for aluminum, they tell us exactly the same thing. We're really not concerned with the inner electrons in the first and second shell for aluminum. It's only the valence shell electrons that will bond, and so that's all we show in the Lewis symbols, and these are certainly the most convenient to use. Page 78, please. Now that we have our symbols and diagrams all ironed out, we can use these to show the formation of bonds between atoms. When atoms gain or lose electrons, they become electrically charged particles called ions. When metals, for example, lose electrons, they form positively charged cations. For example, lithium readily reacts, giving up 1 electron to form a lithium plus 1 cation. We would draw it this way in a chemical formula. Look at our models. Here's the Bohr diagram. Element number 3, 3 protons and 3 electrons, 2 in the inner shell, 1 in the outer shell. When lithium ionizes, only the outer shell electron is gone. We're left with lithium with 3 protons still in the nucleus, but only 2 electrons. The total charge then is plus 1, and here's our electron lost. In our simplified Bohr diagram, we have neutral lithium with 2 plus 1 electrons becoming lithium cation with 2 electrons having lost 1. In our Lewis symbol, we have neutral lithium with a single dot becomes lithium cation with no dots and a plus 1 charge and electron lost. In the case of magnesium, it's in group 2A. It wants to lose 2 electrons. Here's the Bohr diagram. 2 electrons in the valence shell are lost. So initially, as a neutral atom, it had 12 protons and 12 electrons. Now it has 12 protons and 10 electrons, so it has a charge of plus 2. And here are the 2 electrons, or dots, that were lost. In the simplified Bohr diagram, we have magnesium atom, 2, 8, and 2 electrons, becoming magnesium plus 2 cation, 2 and 8 electrons, with 2 electrons lost. In the Lewis symbol, we have magnesium with 2 valence electrons, 2 dots, becoming magnesium plus 2 with no dots. There's the 2 dots that are lost. And finally, with aluminum, it's in group 3A, so it wants to give up 3 valence electrons, forming an aluminum plus 3 cation, like this. And so here's the Bohr diagram. It has 13 electrons in total, 2 and 8 and 3. and then it loses 3, so it's lost its 3 outer dots. Here they are, and what's left is aluminum cation with a +3 charge. Here's the simplified Bohr diagram of aluminum atom with 2, 8, and 3 electrons in the valence shell, and here's the diagram of aluminum cation with 2 and 8 electrons having lost 3, so now it's a charge of +3, it's a cation. And finally, here is the aluminum atom with a Lewis symbol showing 3 dots or 3 electrons in the valence shell, becoming aluminum cation +3 with no dots, and here are those 3 dots. You'll have noticed that the name of the cation is the same as the name of the atom. So this is aluminum atom, this is aluminum cation. But you'll notice when we look at anions next, the ending of the name is changed to an IDE ending. Page 79, please. So on page 79, let's look at the formation of anions. So nonmetal atoms will often gain electrons to form negatively charged ions called anions. For example, fluorine gains 1 electron to fill its valence shell and form a fluoride anion with a charge of -1 in this fashion. Now here it is in the Bohr diagram. Fluorine is element number 9, has 9 valence electrons, 2 in the first shell, 7 in the second shell. It gains 1 more electron to its valence shell, which now has 2 plus 8 electrons, total of 10 electrons in what we call fluoride. 10 electrons, 9 protons, net charge is -1. Here it is a simplified Bohr diagram. So neutral fluorine with 2 electrons in the first shell, 7 in the second, gains 1 more electron to the valence shell. It's now got a full valence shell, total of 10 electrons, 9 protons, the overall charge is -1. It's fluoride. Here it is in the Lewis symbol. Neutral fluorine atom gains 1 more dot or 1 more electron to the valence shell, and therefore it is a charge of -1 because now it has 1 more negative charge than it had when it was neutral. How about oxygen? Group 6A. It would like to gain 2 electrons to get 8 electrons in the valence shell, and so doing it becomes an oxide anion with a charge of -2, like this. How about the Bohr diagram? Element number 8 with 8 protons, 2 in the first shell, 6 in the valence shell. If it gains 2 more electrons to the valence shell, it now has 8 in the valence shell and 2 in the inner shell, grand total of 10. That's 2 more electrons than protons. Its charge is -2. The valence shell is full. It's an oxide anion. Here's the simplified Bohr diagram. Neutral oxygen with 8 electrons, 2 in the first shell, 6 in the second shell, gaining 2 more electrons to the valence shell, forms an oxide anion, still with 8 protons, but now it's got a total of 10 electrons, so that's a charge of -2. And here is an oxygen atom in its Lewis symbol with 6 dots, gaining 2 more dots or electrons to the valence shell becomes an oxide anion with a full valence shell of 8 electrons and a charge of -2. And finally nitrogen, which is in group 5A. Non-metal would like to gain 3 electrons to fill the valence shell and form a nitride -3 anion, like this. So here it is in a Bohr diagram. Element number 7 has 7 protons and 7 electrons, 2 electrons in the first shell, 5 in the valence shell. If it gained 3 more electrons to the valence shell, it would now have 8 electrons in the valence shell and a grand total of 10 electrons, but only 7 protons, so the charge is -3. Here's a simplified Bohr diagram. A neutral nitrogen atom with a grand total of 7 electrons, 2 in the first shell, 5 in the valence shell, gaining 3 more electrons to the valence shell. Now it has a full valence shell, 2 electrons plus 8 is 10, 7 protons, the charge is -3, that's a nitride anion. And finally nitrogen Lewis symbol of the atom with 5 dots, could gain 3 more dots or electrons to the valence shell, forming a nitride anion with 8 dots in the valence shell, or 8 electrons, and a charge of -3. So you may have noticed the pattern that early chemists discovered. When metals form ions, they usually empty their valence shell by losing valence outer electrons. That's for metals, right? after which they have the same electron configuration as the nearest noble gas. They don't become noble gases, they don't have the same number of protons, but they have the same number of electrons in the valence shell. And the term for that is that they become isoelectronic. And iso means the same, and electronic refers to electron configuration. They become isoelectronic with the nearest noble gas. Recall that noble gases are stable, inert, unreactive atoms. They have valence shells that are full of electrons, 2 in the case of helium, and 8 for the other noble gases, neon, argon, krypton, xenon, etc. And it is consistent with the laws of nature that systems will spontaneously move towards more stable, lower energy states. So what we're saying is there is a tendency for these elements that are close to the noble gas to either gain electrons to fill their valence shell if they're nonmetals, or lose electrons to empty their valence shell if they are metals. And that's what we observe. Nonmetals usually gain sufficient electrons to fill their valence shells to become isoelectronic with the nearest noble gas. And note again that the anion names have the front part of the atom's name but end in "ide." So this is nitrogen and this is nitride. Oxygen, oxide. Right? And this is fluorine, and then the anion is fluoride. So we add the IDE ending to it. Page 80, please. So on page 80, I've drawn the simplified Bohr diagrams and the Lewis symbols to try and emphasize one point. I've put groups 5, 6, and 7 on the left, and then 8 in the middle, and then 1, 2, and 3, the metals, on the right. When the nonmetals gain enough electrons to fill their valence shell, and when the metals lose enough electrons to empty the valence shell, they are then isoelectronic with the nearest noble gas. The nearest noble gas to nitrogen is neon, which has an electron configuration of 2 and 8. The nearest noble gas to oxygen is neon. The nearest noble gas to fluorine is neon. The nearest noble gas to sodium is neon. The nearest noble gas to magnesium is neon. The nearest noble gas to aluminum is neon. So look what happens. The nonmetals fill their valence shell 2 and 8, 2 and 8, 2 and 8, 2 and 8 looks isoelectronic with neon 2 and 8. Now they're not the same, right? These are not identical. There's a different number of protons. Neon has 10 protons, fluoride has 9. So fluoride is not neon, but they are isoelectronic. They have the same electron configuration in their outer shells. Likewise, sodium, when it loses its valence electron, it's isoelectronic with neon. Magnesium loses 2 valence electrons to become isoelectronic with neon, and aluminum loses 3 valence electrons to become isoelectronic. Now, one thing you should note here, for Lewis symbols, we have nitrogen with 5 dots becomes nitride with 8 dots, which is isoelectronic with neon, which is 8 dots in the valence shell. Oxygen with 6 dots gains 2 dots to become oxide, isoelectronic with neon. Fluorine with 7 dots gains a dot, charge of -1, fluoride anion, isoelectronic with neon. But look at sodium. Sodium has 1 dot, it loses that, and a sodium plus. We do not draw the dots for the next inner shell of electrons. We don't draw the dots for the inner shell. So these are isoelectronic, but the symbols may not look it, but they are in fact the same. So magnesium, with 2 dots in the valence shell, loses those 2. It is now isoelectronic with neon. Now again, they don't look isoelectronic, but in fact they are. Magnesium plus 2 ion will have 8 electrons in the second shell, just like neon does. And aluminum with 3 dots loses those 3 dots, and we just draw aluminum plus 3. Page 81, please. So page 81 brings us back to where we started in the course, learning about charge and oxidation number. So here I have the noble gases in the middle. What we're saying here is that the charge of the group 1A metals will always be +1. I don't think there's any exceptions. If group 1A metals are going to be charged, they'll be +1. Likewise, group 2A. If they're going to form an ion, they'll always be +2. Group 3A metals, if they're going to lose electrons, they're most likely going to be, or exclusively be, +3. Group 4A metals will exclusively or likely be +4. The group 7a nonmetals, if they're going to be an ion, they can only be -1 when they gain that 1 electron to fill the valence shell. The group 6a elements, if they're going to be ions, they're almost exclusively -2 as they gain 2 electrons to fill the valence shell to become isoelectronic with the nearest noble gas. The group 5a nonmetals, if they're going to become ions, they're typically going to be -3 when they gain 3 electrons to become isoelectronic with the nearest noble gas. In the case of bismuth, it's a weak metal, so it does show an oxidation state of +5. Now I've left out the metalloids here, they're shaded gray, and left out carbon because they rarely form ions. So I trust this is crystal clear now. You should be very familiar with the most common charges of the representative elements as ions. And the last page, page 82, please. So on page 82 we are closing with a revisit of periodicity, or the periodic law, which says that properties of elements repeat in regular patterns. That is, elements in the same vertical columns or groups will have similar chemical properties. This is particularly true of groups 1a and 2a, groups 7a and 8a. The alkali metals, the alkaline earths, the halogens, and the noble gases. In the middle A group families, groups 3a, 4a, 5a, and even 6a, the similarities going down the column are sometimes outweighed by a transition from non-metallic at the top of the column to metallic character towards the bottom. Similarities within a vertical column can be attributed to similar electron configuration in the valence shell of all the atoms in the group. So let's conclude with this. From this we can say the noble gases, group 8a, have valence shells that are full of electrons. They are inert, stable, and unreactive. They do not gain, lose, or share electrons. The halogens of group 7a have valence shells that are 1 electron short of being filled, and they often react by gaining 1 electron, forming a -1 anion. The alkali metals of group 1a are all very reactive. They readily lose 1 electron, forming +1 cations. And the alkaline earths of group 2a are moderately reactive. They readily lose 2 electrons, forming +2 cations. And that's it for this first part of chapter 3. I apologize for the simplicity of this, but it's absolutely imperative that you do have this basic understanding so we can move forward with bonding.